I will speak about the voice regarded as a musical instrument, and this is what the dishes I'm going to serve you. How does it work? And then the noble art of getting heard, and then some word of how to get the performance interesting, catching the interest, the attention of the audience. Now the instrument, this will be a repeat for some of you. The lungs is a compressor. It produces an overpressure of air like in wind instruments. And this air is passed through a narrow slit with very mobile walls, which are called the vocal folds. And the result is that the vocal folds start to vibrate and then open and close the valve to the overpressure downstairs, and that then creates a pulse train, like something like this, but very much faster. So if you sing 440 hertz, that should have been 440 puffs per second. Okay, one of the miracles of our lives is that such signals repeating themselves at high rates are constituted by a set of a chord of simultaneously sounding overtones. So we have this signal is contains a fundamental with the pitch of which we hear as pitch, and then the second partial, which is 1 octave higher, and then the fifth, and then the fourth, and then so on. On all these partials, they try to swim through the vocal tract, but the vocal tract is a crazy equalizer with peaks and valleys in between them, and the peaks are created by the resonances in the vocal tract. And so some people who try to get through, like the fundamental in this case, hit a valley in the frequency curve of this vocal tract, and then it comes out as a weak partial in the sound radiated from the mouth. And the second partial in this example hits the peak, the first peak, so it comes out as a loud partial. So the frequency curve of the vocal tract forms the shape of the spectrum of these things that I will keep talking about this for a while, so if you don't understand what I'm telling you, try next time. Okay. This is the waveform that I showed in the previous slide, and you could hear how it sounds. It sounds like this. So this is the sound that you would hear of my voice if you took off my head. It's the head-free voice. Okay, I could also play you a vowel sound here, but not as a chord first, but as an arpeggio. First the partial, then first the first partial, second, third, and so on, in an arpeggio fashion. And then at the end they come as a chord. Isn't that remarkable? If we play all these partials together, it becomes not at all a chord, it becomes a vowel sound. Okay, now let's see a sine wave through a tube. We will make this experiment for you. We take a tube like this, and then we take a tone like this. It's an earphone, and I will now disconnect the loudspeaker system and insert this instead, and try to find a hole, and then we should get off this presentation, and I will take a program called a tone generator somewhere here, there, and I could then send the tone through the I don't think you hear very much of it, but maybe if I keep it. Hörru. Så här. Yeah, you hear that there's a tone. This tone is now going to travel like one of the partials in the voice through the tube, and then you should expect to hear that the tone becomes very loud at some points and soft at other points. And if we are lucky, I could manage to convince you about this. So here is the microphone, and let's start at the low frequency. And the low frequency is now going to be somewhere here. Okay, and then no. Here it's a bit louder there, and if I go higher it becomes softer. And then there is another resonance. Quite loud. And you have third. There you have more ones. So what I did now was just to insert, do this experiment. I took a tone. It was gliding from low to high frequencies. I reconnect the loudspeakers now, and then you heard that the sound became loud, and that was because of resonance. And the spectrum peaks occurs at the resonance frequencies of the vocal tract. Now you may want to listen to a pulsating airflow also that you could receive by buying a duck call, because the duck call is a tube, and it has a very mobile membrane here, and when you blow here, the membrane opens and closes the way for the airflow. So you get the pulsating airflow. It sounds like this. And if I connect that to the resonator that we just tested, it won't sound like this, but it will sound like a vowel, because it is a pulsating airflow that travels through a resonator. Yes. So that is, as soon as you shape this spectrum with peaks and valleys, you get the vowel quality. Formant frequencies, the resonance frequencies of the vocal tract, they are determined by the shape of the vocal tract, and the shape may be very varied. You know, if you say an E, we feel that the tongue is visiting the mouth, because we could feel it there. And when we say ooh, it actually, we don't feel where it is, but I tell you the truth, it is sitting up here in the corner below the velum, lip, lower front teeth. And when I say O, it is further down in the pharynx, and when I say A, it is very far down in the pharynx. And when I say E and E, I use almost the same vocal tongue shape, but the jaw opening is a bit wider in E than it is in E. Okay, now you want to see a demonstration where I deform the vocal tract, but this is very difficult to do without breaking the plastic tube. So I bought a hose instead, and I could squeeze it at different points. And that means that I shape, the tube is assuming different shapes, and hence the resonance frequencies are moving as in the vocal tract. So let me start with a cylindrical tube, which is actually sound when the vocal tract shape that we use when we do not know what to say. We say then. Yes, and but when we are more filled with communication urge, we form the vocal tract in various shapes. So, for instance, we squeeze the tube in the pharyngeal end, or in the mouth end, or we shift between a pharyngeal and a mouth oral constriction, which we say actually when we agree in Sweden. Ja, ja, ja. Mm-hmm. We have a code that is secret, but phoneticians knows about it. The frequency of the first resonance peak in the vocal tract, the first formant, and the second formant. The combination of first and second formant define what vowel which is going to be produced. So if we have the first formant at 300 hertz and the second at 700 hertz, we will get oo, like in hood. And if we have it the first at 800 hertz and the second at sometimes something like 1200 hertz, we will get A. And here we have A and E. So this is difficult to believe, so I thought that I should convince you by doing this experiment live. I do have setting here called the F1, F2 map, and I could make it similar in size and similar in range as the one you have there. And then we could check the truth of what I just said. I said 300 hertz and 700 hertz will produce the vowel A. So where are we now? And then, okay, I need to do get these things together. So here we go. Yes. 300 hertz. No, you see, I was lying. 300 hertz and 700 is O. And then if I go to 900 and 1200, I said, and here we have, and then, yeah, we could do that as thank you very much. Okay, so this is the secret of these formant plots. So if they tune the two lowest resonances of the vocal tract to a low frequency, we get U. If they have first formant, first resonant at 800, second at 10 or 1200, we get A, and here up here we get E. So we made a crusade in this archipelago, and as a result, we met most of the vowels that we could use in languages. I will show you another thing also. I said that the vocal tract's shape determines where the resonance frequency is going to be. And here we have a guy with an I, and we could listen to what the vowel will be with this kind of vocal tract, articulatory shape. Is what he would say here. But I could move the tongue and make it a front constriction, and then very good Y, and if I spread the lips, I get some more, perhaps a bit more jaw opening. How about that? And some more. There we are, E. And back here I should get the A vowel with a pharyngeal constriction. Yeah, Stockholm A. And if we make it wider, a bit better, and so on. And there is the A. Okay, and I could neutralize the tongue and get different vowels. So this is a demonstration of the meaning of the articulatory tools, the tools that we have to shape the vocal tract in various ways in order to place the formants to various frequencies, and that means to produce different vowels. This is a spectrogram where we show the time along the frequency, along the horizontal axis, and this axis is actually the frequency, and here the gray scale is loudness. So here you could see that this frequency range was strong here, and then it shifted down to a lower frequency, and this is another strong frequency range, and that shifted in frequency to a higher position. And what I said here was A, I, U, actually. So you could visualize speech and singing in this simple way. The formant frequencies, the formants are also crucial to the consonants. So in order to convey consonants, look at this. Here we have B as in bed, and D as in David, and G as in Gustav. And here we have, you see that the second and third formants bow down in order for the occlusion, and then go back to their original position. And D, they do different things. This one goes down, and this one goes up, and then back again. And here they go to meet each other for producing the G. So you could say that the trick to produce consonants, that is to fix the higher formants and to be precise with the vocal tract shape for tuning these formants, and also to have sound energy up there at these very high frequencies, 2,000, 3,000 hertz.
So if you speak like this, you don't get very much performance.
Because you don't have any high partials in your voice. This is an example of this. Here, two people were, Smith and Scott, were asking a panel, what vowel is this? And here it was vowels only, and here is the pitch frequency. And this is F4, and this is F5. So this is the top F for an alto voice. And you could see that from the C, well, the recognition, the intelligibility is fair up to C, and then deteriorates up to F, and then it is almost impossible. However, if you add consonants, you improve the situation very much. So in order to hear what the vowel is at high frequencies, you need consonants, otherwise you won't be very successful. Vocal tract length is also important for the formant frequencies, and short vocal tract length have higher resonance frequencies than longer. I refer to my friend the organ. You see, in order to produce low tones, you need long pipes, and short tones should be produced by short pipes. And the same is true for vocal tracts. So you remember this vocal tract length is, yes, that is that. And if I then combine that voice source with a shorter vocal tract, it's just half of it, and then I get I still get something similar in vowel timbre. But the person with this voice, I don't think I ever met. I met more of people with shorter vocal folds, and they have higher pitches. So that means more of a child. So the characteristic of a child voice is that it has a short vocal tract and short vocal folds. And that gives higher resonance frequencies in the vocal tract and higher pitch. Okay, this is a summary. If you want to change your first formant, the jaw opening is very good as a tool. If you want to manipulate the second, the tongue shape is very good. And then the third formant is sensitive to a cavity. So when you say here in the United States of America, you pull the tongue back and get a big cavity, and down goes the third formant to 1500 hertz. It's very efficient. And the higher formants are more larynx position, vocal tract length, and so on. Yeah, conclusions. Articulation, that controls the vocal tract shape, and the vocal tract shape determines the resonance frequencies of the vocal tract that are called formants, and they determine the vowel quality. And the higher formants are relevant to the personal voice quality that I will speak about a bit right now, I guess. Getting heard, namely, portion number 2. The male case, the singers of male gender they produce a high spectrum peak that is being called the singer's formant cluster or the singer spectrum peak. And it is a question of the fine art of clustering higher resonances in your vocal tract. It is found in tenors, baritones, and basses. You could check the spectrum if we look at the spectrum. I have a... No, that was not it. There. Okay, and the microphone, and it should be turned on. Yes, it is on. And now let's see. This will show you the spectrum. I have frequency here and loudness there. And that's how the spectrum works. Now, I will produce the vowel oo as I would do it in speech, ooh, and as I will do it if I would sing in a classical style, ooh, ooh. So you see that there is a mountain of strong partials here in the high frequency range, and that is typical of all these people who are of male sex and sing with the singer's formant spectrum. Okay, it has a very good payoff because you get heard if you have loud orchestral accompaniment. The background is that orchestras, when they play in the Western countries, not in China, but here in the Western countries, the partials in the low frequency range, in the bass range, they are very loud. And then when you come up to 700 hertz, high F for alto voices, then it starts to decrease. So when you have reached the region of the singer's formant cluster, as here at around 3 kilohertz, the competition with the orchestral accompaniment is not all that difficult. Listen to this sound. It is a noise filtered so as to have the same sound properties as the orchestra. Then comes a singer without the singer's formant cluster and with the singer's formant cluster, and then I combine the noise and this singer without and with the singer's formant. I will point by one. And there's now the singer without.
Gamla du fria,
And now with.
gamla du fria, du gamla du fria, du gamla du fria, du gamla du fria, du gamla du fria.
And now with the noise. Simple as this. You hear the singer's voice much better if it has a singer's formant in the competition with an orchestral accompaniment. The tricks for achieving a singer's formant cluster is to have a good voice quality, a nice closure of the vocal folds, a wide pharynx that you could achieve with a low larynx, and that produces a clustering of the formants number 3, 4, and 5, because formants are like friends. If they come close together, they gain in strength. And you could see an example here where I moved the fifth formant down to that in the blue case, and the fourth formant down to this position, so that the third, fourth, and fifth formant form the cluster. And that gives the resonance, and you don't need to pay any money or any effort in order to get it. You just get it for free. And that is, of course, a very great, smart thing to do if you'd want to save your voice. But now, let's see. Any peak in the high frequencies is not a singer's formant cluster. Here I have a very good example. The red one is a musical theater singer. They don't sing with a singer's formant because it sounds so very remarkable. But they have a little peak here, typically 1,000 higher in the 3,500 rather than 2,500. This is a baritone singer from the Stockholm Opera, and he has a very high marked singer's formant cluster as expected. But what is this? It's an in-between case. And you would be astonished and quite convinced that this is not the singer's formant when you hear the sound. Okay. So any peak in this region doesn't mean a singer's formant. Let's look at females and males. Here is an average spectrum of 4 baritone basses and tenors and altos and sopranos. And you could see that they have much more of energy here in the 2,000 to 3,000 area than the female singers. And I think female singers would sound very queer if they had a singer's formant cluster. Okay, the center frequency of the singer formant could move a bit, and that is very important for perceptual reason. Let's look at the facts. Here is the bass. Basses typically have a bit lower singer's formant center frequency than the baritones, which have a bit lower than the tenors. And you should listen now to the effects of these changes. I will change here the singers. First I will make a singer's formant of this, and we should have a nice vowel. Let me yeah, that was not so nice, but I could do yeah, something like that. Okay, and we add a bit more of vibrato. This is very little, and then some kind of here. Okay, now I will cluster formants number 3, 4, and 5. I start this with at 2,100 hertz, and you hear already that it's a rather big guy. And the 3rd, 4th formant is now approaching, and you could hear that it adds a voice quality that you recognize from singers' voices, classically trained. And then the 5th formant is sailing down, and it will soon be there. This is about thing. Yes, so this is okay, and now I will shift this singer's formant cluster mid-frequency 200 hertz higher, and listen to how it affects the tone. Here we go. And look at this. And look at this. You have it quite different. And now 200 hertz more. And here. And here. So you hear that the center frequency of the singer's formant is quite important to the voice quality. Yes. Another demonstration of the same thing. Here is Jussi Björling, a late Swedish tenor, singing from Aida.
Sei quel guerriero fossi, sei il mio sogno savera sé.
And then I took his 3rd formant in this recording and turned it down in frequency a couple of hundred hertz. And then you get this.
Sei quel guerriero fossi, sei il mio sogno savera sé.
Instead of
sei quel guerriero fossi, sei il mio sogno savera sé.
So again, the center frequency of the singer's formant cluster is quite crucial to what voice quality you are going to get. Now, where do you get that voice quality from? It turns out that it is the length of the vocal tract that is crucial to this, it seems, at least the dimensions of the vocal tract. There was in Dresden, Germany, they had accumulated during the communist time X-ray profiles of singers. All the people that went into the solo singer education class, they were X-rayed. So there was a huge material, hundreds of X-ray. And Friederike Röhrs was doing her dissertation work on this, and we published this jointly in this year. What she was measuring was the length of the oral cavity, defined as this, and the corner cavity, and then the pharyngeal length. This is her results. This is vocal fold length and voice classification. Sopranos, trachea diameter, which is equivalent to the vocal fold length. So sopranos have short vocal folds, and then as you go down in the frequent pitch ranges, you meet more and more long vocal folds. That is this is typical for singers. And if you look at the division here between sopranos, mezzo-sopranos, and so on, you see that the soprano points are down here. Vocal fold length there, vocal tract length there, so that the sopranos are short in vocal fold length and the basses are the ones that have long vocal folds. What about the vocal tract then? Well, the vocal tract also varies systematically with voice classification. So sopranos tend to have short vocal tracts and basses tend to have long vocal tracts, and the intermediate voice classifications, intermediate voice vocal tract lengths. And what is the reason for this? Well, it turns out that it's not so much dependent on the mouth lengths, because there is not so much difference between different voice classifications. But in this, the pharynx length, there we find it. So if you find a person with a very short pharynx, your first guess should be soprano. And if you find someone with a long pharynx, a long distance from the corner here and to the Adam's apple, it should be a bass according to these findings, or the likelihood at least. Okay. And then we also had some other materials that we could look into, for instance, body height. So would it be likely that I would be a soprano? Not really, but it is not a significant factor. So that has nothing to do with the classification. And what about body mass index? Fat people and thin people, does that have an influence? And the answer is by no means. There could be thin basses and fat sopranos. Okay, so singer's formant cluster, if you summarize, it occurs near between 2,000 and 3,000 hertz in tenors, baritones, and bass voices. And its center frequencies varies with voice classification and is very important to the voice timbre, the personal voice timbre. It is generated by putting together, clustering the resonances number 3, 4, and 5 in the vocal tract, and it can be achieved by a wide pharynx and a lowered larynx, and it helps the male solo singers to get cut through the loud orchestral accompaniment. And is this, as this is a resonatory phenomenon, it is a case of vocal economy, which is very, very likely to find among successful vocal users, voice users. Let me now talk some about the expressivity. I think you all have noticed that if you push a button and play music reproduced by a computer, put the score in and have it played by the computer like you could do in Finale or in Sibelius or these other programs. It sounds quite pathological. Nobody would play it like this. It sounds awful, actually. Because it lacks expressivity. And it reproduces quite verbatim the music score as it is written. But what the questions we have been asking in this investigations is what is the code for expressivity in music performance, and where did we pick up this code? This is the toolbox that we have been developing at KTH. We have a music file. It goes into a computer where Director Musices is the program, but performance grammar, and it controls a synthesizer. So we get the synthesis of the performance stored in the music file, and here we have the tremendous privilege to have a wonderful musician, Lars Fridén, who was a violinist and music pedagogue, sitting with us and listening to the synthesized performances and commenting upon what was wrong with it. And he made recommendations that I and Anders Friberg, my colleague, was then translating into new performance rules that we inserted into the performance grammar. And then we tried the same example and listened to if it was better or worse, and acted accordingly. This is the program that you also could download from the internet. It's called the Director Musices, and there is a lot of rules, and you have sliders here, so you could take the high-loud rule in extremely exaggerated quantity, or you could revert it, and so that the higher pitches are played softer. This rule increases loudness with pitch, and you could, if you go to the negative side, it will decreases. And melodic charge and harmonic charge and what have you. I will talk about three main principles that we have found in these performance principles. One is the marking of structure, which is called phrasing. One is the sharpening of contrast, which seems to be called nothing. And one is to emphasize important notes, which is probably called accents or something. Okay, mark the structure. Here I asked the Swedish baritone Håkan Hagegård to perform a set of music examples as void of musical performances as he could, and then as in a concert. Here's an example of his neutral, his unmusical performance of an example from Mendelssohn's Paulus.
Gud var mig nådig.
And here are the performed to nominal tone duration. So if he lengthens a note, the syllable will come up here. So this is a very much lengthened note, and here they are shortened. Okay, again. Hördu.
Gud var mig nådig efter din godhet. Utplåna mina synder efter din stora barmhärtighet.
And when he So he made lots of changes in the tempo depending on where he was in the phrase. Gud var mig nådig, one phrase, efter din godhet, the second phrase, and they belong to the same unit, so they are two sub-phrases that construct a phrase. That's the end of it, and he marked that with lengthening of the notes. Okay, and when he did it in an expressive manner, it was even more.
Gud var mig nådig efter din godhet. Utplåna mina synder efter din stora barmhärtighet.
Okay, so here you see a phrase pattern. Start, speed up, and then slow down towards the end of the phrase. And you do it even more when you come to a phrase than you do when you come to a sub-phrase ending. So tempo change, I would like to introduce to you the term expressor. Tempo change, these tempo changes are an expressor because they express something that you, namely where you are in the phrase. And the interesting thing is that this is not exotic. We find it in speech also. This is an example. Here I said sasasas, which doesn't mean anything, but anyway, sasasas. This is the stressed syllable in initial position. And then when I said it in the final position, it's much, much longer. Sasasas. So I mark the end of the unit by lengthening the last element of it, just as in the musical case of the phrase. So And what could the origin of this expressor be? That slowing down, lengthening means the end of the unit. Let's think about pianists. They need to move their hands like this, and it turns out when they do that, they follow a certain velocity curve. This is the velocity curve that human limbs follow when we move from one place to the other. It is highest speed in the middle of the movement, and then we brake when you turn on the step on the brakes to slow it down to reach the target. Okay, and of course this is similar to we could then switch the relative velocity and the position in the room to a relative tempo and note position in the phrase. Okay, and then we talked about not so much tempo, but we talked about duration. At least I did. And then we get this kind of structure, and that is very similar, of course, to the phrasing curve, the tempo curve of the phrases. Here you see it applied to a simple example. Bam ba dam bam ba 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 da dee da 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 dum ba da 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 pa 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 pa, and so on. Nursery tune in Swedish. So this is a subphrase, and this is a subphrase. They go together to form a phrase. Subphrase, hand movement derived phrase tempo curve for the subphrase number 1 and for subphrase number 2, and then you add the phrase phrasing curve for the phrase, and then you get this da 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 ding da 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 dim. So okay. And if you apply these simple principles to the Hagegård example that we just see, Gud var mig nådig efter din godhet, we get this curve, which is quite similar. So I would argue that we get we got the idea to mark phrases from our experiences of human motion, locomotion, hand motion. Another example, even more inspiring, this is the average final ritardando. This is how the tempo is decreased in commercial recordings of motoric music with some kind of pulse going into it. Okay, and this is the normalized, this is full tempo and this is full stop. Here is the beginning of the ritardando time, and here is the end of the ritardando time. Now, we rented 4 professional dancers and asked them, now run here from this point to this point, and you should stop there, and you should have this tempo on your step, or you should have this tempo on your step, or you should have this tempo of your steps. And how did they do the stopping? Because I thought that the ritardando must be a portrait of running stopping runners. But it wasn't. Actually, the normalized velocity of the runners, this is the red curves. And the blue curves are still the mean ritardando curve. They agree perfectly. So the final ritardando we use in music is a portrait of the velocity decrease when a runner is stopping. And then it would be easy to understand what it means, of course. So that would help the understanding of music performance. So do we understand tempo changes, tempo change expressor, because they allude to our experience of human motion or animal motion also? Principle number 2, sharpen the contrast. The case of pitch is fascinating. Listen to this, and the tuning. How nice is the tuning of this? Well, people don't like that because they think it's dull in the top. If we stretch the tuning a bit and make the high pitches a bit sharp, we could make it even more. Yeah, it's funny. You shouldn't do it too much, but you must do it, because otherwise it sounds as if you are not wanting to play the piece that you are playing. We could do... The interesting thing is, listen to this once more. And now we do the opposite. Exactly 20 cents sharpening of the peak pitches. We flatten the peak pitches. So this curve is inversed here. And then we get this. So it's completely impossible. Nobody would accept that kind of intonation. And it was just as much, but the wrong sign. Okay, another example, even more fantastic. Jussi Björling again. This is the example he was singing.
Dirti per te ho pugnato, per te ho vinto.
And this is the intonation curve. Here you see the pitch. Okay, so I wanted to correct the pitch because it is 70 cents sharp here. On average, it is 70 cents, more than quarter tone too sharp, as referred to the equally tempered tuning. So here I put in a synthesized. Madde helped me to make this synthesized top pitch.
Dirti per te ho pugnato, per te ho vinto.
Okay, and then I could correct it and play it in equally tempered tuning.
Dirti per te ho pugnato, per te ho vinto.
Problematic. So it seems that we expect the peak pitch of a rising phrase to be a bit sharp. Otherwise it sounds out of tune. Yeah. So remember what happens in the recording studios to these. They have machines where they correct the intonation of the pop singers and make it agree with the equally tempered tuning. So they rip them of some expressivity if they are good singers. Okay, now where does this expressor come from to exaggerate the differences? I think it is used also in speech. Here you see an example. This is the formant frequency of long E in Swedish and short E. So the long E and I, they differ in duration. One is long, one is short. But this is not enough. The contrast in duration is exaggerated by adding another difference to them, and that is the vowel formant frequencies. So these are just two examples. You see that the vowel formant frequencies in a long and short E is not the same, and the same is true for the R. Okay, so that the sharpening of contrast is a principle that is used also in spoken communication and in other types of communication as well. Now, principle 3 is to emphasize the important events, which is very important in order to keep an audience awake, actually. The onset of a tone is crucial in this business, and we made an analysis and measured the time interval between the vowel onset of the singer and the chord onset of the accompaniment in piano accompaniment solo music. Okay, and there was many examples of a bit lagging or a bit leading, depending on expressive color of the performance. But the most common was 0 milliseconds between the onset of the piano chord and the onset of the singer's vowel. So it's obvious that the sung tone starts with the vowels. You can't start with an S. You must have the onset of the vowel to come on the beat. Okay, so that is it. Now, what the expressor in singing is the timing of tone onset at the tone duration. Let us now look at the durations in Hagegård's material. Here you see from Dichterliebe es schweben Blumen, how he departed from the nominal duration of the various tones in this example. And when he sang it with expressive color, the departures were very much longer. Now listen to this first, the neutral, and then the expressive.
Es schweben Blumen und Englein unsere liebe Frau, die Augen, die Lippen, die Wänglein, die gleichen der Liebsten genau.
And then the concert version.
Es schweben Blumen und Englein unsere liebe Frau, die Augen, die Lippen, die Wänglein, die gleichen der Liebsten genau.
Which is interesting because he doesn't lengthen the stressed syllable, but he lengthens the upbeat to the stressed syllables. Unsere Liebe, what is being lengthened here is not Liebe, but the upbeat to unsere Liebe is what he does. Okay, and here you have another die Lippen, where die is the thing that is being lengthened, and genau now has this main stress, but the precursor, the syllable, the upbeat to the stressed is being lengthened. So that's funny. And where did we get that from? Actually, it could be called emphasis by delayed arrival. And that seems to be a phenomenon that we have seen in many connections. The person who's coming late to the lecture is always catching the attention more than the speaker. Okay, and in syllable duration in speech, you have the same phenomenon. I went to an actor, asked her to pronounce the phrase on Tuesday, he should tidy. In Swedish, på tisdag ska han städa, and asked her first to no particular stressing, but then stressing this syllable, på tisdag, and på tisdag ska han städa, and på tisdag ska han städa. Okay, and this is the durations of her syllables, and here is the sound.
På tisdag ska han städa.
And
På tisdag ska han städa. På tisdag ska han städa. På tisdag ska han städa.
so she does exactly the same as Hagegård did in the expressive versions. Lengthen the upbeat to the stressed syllable, and that will catch the attention of the audience. So emphasis by delayed arrival is an expressor also in speech. So summarizing then, the instrument, well, we have a pulsating transglottal airflow. It is controlled by subglottal pressure, the glottal adduction, how much you squeeze the vocal folds together, and the vocal fold length and tension. That is the way you control the pitch. And the instrument is also characterized by the formant frequencies, the resonance frequencies of the vocal tract, and they are called by controlled by articulation, and control the timbre, your vowel, and your personal voice quality. To get heard, you use formants to reach audibility when the accompaniment is loud, and that is also actually a principle that is used by female singers, but in other manners. And then for expression, it is important to mark the structure, to enhance the contrast, and to emphasize important events. And that is the end of what I would like to say today, unless you have a question or two to me. Okay, thank you.